couple of things about your graphs. So first of all, trends that you noticed. Okay. So what happened when we went from graph number 1 to graph number 2? Okay, it just flipped. What do we call that in our transformation language? It was reflected vertically or horizontally? Vertically. It went from going up, and then all of a sudden that part that was shooting up was shooting downward, right? Okay, so that's a vertical reflection. It shouldn't be that surprising that multiplying by a negative outside of the exponent part is a vertical reflection, because negatives outside of our function out in front always did that vertical reflection thing. Okay. All right, what happened when we changed the exponent to x plus 4 instead of just being an x? So how does the third graph compare to the first graph? Okay, all of a sudden it doesn't cross at 0, 1, right? So what did happen? Okay, it crossed at 0, 16. So when you plug in 0 to the third equation, you get 16. Where do you think that 0, 1 point went? So, okay, good. So Ryan says for that way, like to the left. So if I plug in negative 4 to this function, that's what would now make the exponent equal to 0, right? And then that's where the 1 point went. So adding or subtracting something up here is shifting the graph to the left or to the right, that now all of a sudden the point's not at 0, 1. It's at negative 4, 1, and at 0 it's reaching all the way up to 16. It shouldn't be that surprising that adding or subtracting something in the function, in the exponent area, shifts it left and right, right? Just like it did underneath a radical or stuff like that, okay? What happened when we changed it to a 1/3 instead of a 2? So what was the difference between graph number 1 and graph number 4? Okay, it got more narrow. Okay, what else? In the first graph, as x got bigger, the graph got bigger, right? And as x got smaller, it got closer and closer to 0. Is that same thing true with 1/3? No. What happened as x got bigger? So look at your sketch. For 2 to the x, we had like this idea where it crossed at 0, 1. As it got bigger, it got bigger. As it got smaller, it got closer and closer to being 0. When you graphed 1/3 to the power of x, how did the graph look different? Good. So it still hit at 0, 1, right? But kind of went the other direction. Smaller numbers being plugged in actually made the graph get bigger. And as the numbers got bigger that we plugged in, the graph got closer and closer to 0. Any idea why that might have happened? What's different about those functions? They're both just taking a number and raising it to the power of x. Okay, good. So it's not a whole number, it's a fraction. So this kind of tends to be the trend if our base is bigger than 1. But if our base is smaller than 1, this kind of tends to be the trend. Okay? All right, what about number 4? If we put a negative in front of the 1/3 power of x, what happened? Okay, so it goes down, right? So it should just be a reflection. If you look at the graph in number 4, oh, there's 2 number 4s, that's sad. In number 4a and number 4b, then you should see they're just reflections of each other, right? One's above the axis where one is below the axis. Okay. So again, that negative still does the same thing. It's just that this graph started off a little bit different. What happened when you did this like +3 at the end of the function? Not in the exponent anymore, just kind of like outside. Kristen? Okay, so the graph seemed to flatten out a little bit more. Okay, what number did it seem to flatten out now that you added this +3 at the end? At 2? At 3. It should. So what should have happened is the picture that you saw in the second part of number 4 here. This should be almost the exact same picture, except for the whole graph shifted up 3. So instead of it getting closer and closer to 0 like it would here, this whole graph would be moved up 3 spaces, and it would be getting closer and closer to 3. Because it's the entire same function that we had before, right? The only thing we did was add 3 at the end, so that's the effect it would have on the graph. Now remember, in our previous functions, adding something outside of the function was a shift vertically up and down. It's still going to serve that same purpose in these functions here. Okay. All right, and then finally in graph number 6, it was basically the same thing as the very first thing we graphed, but I changed the base from a 2 to a 5. How did that affect the graph? So compare the very last thing you graphed, y equals 5 to the power of x, to the very first thing that you graphed. Did it still cross through the point 0, 1? Yes. Okay. Was everything else about it the same? So go back and look at, so this was your first graph, 2 to the power of x. How do you think 5 to the power of x compares to this? So if we graph 5 to the power of x, somebody told me it still has the point 0, 1. Okay. Is it still getting bigger and bigger on one side and closer to 0 on the other side? Oh, look at your graph. Graph it on a graphing calculator. People have it sketched. Does it look very similar to the first one or no? No? Feel like it looks very different? Then explain to me what it looks like. Steeper? Okay, so it still should be getting closer to 0 on this side. And it should still be climbing on this side. Okay, but Ryan's right, it's going to be steeper. The reason it's going to be steeper is if we take 1 as an x value. If we plug 1 into this function, 2 to the first power is going to be 2. So you're getting the point like 1 comma 2. Okay? But if we plug 1 into this function, 5 to the power of 1 is going to be 5 just to the first power. It's going to be 5. So instead of being this high, it's going to be this high. So this graph is going something like this. Okay? So the only thing that's going to be different about studying these exponential functions, obviously their shape's going to be different. You saw a new shaped graph than the stuff you've seen before. Multiplying by a is going to kind of do the same thing. You saw how the negative would flip it upside down, so it would be a vertical reflection. Adding, subtracting stuff in here is still going to be horizontal changes. So all the horizontal changes are going to take place in the exponent. Adding and subtracting moves things left and right. Okay. Out here, adding and subtracting stuff is going to move it up and down. But there's an extra component to these problems, and the extra component is you can change this number, and even though they have the same general shape, like they have this one special point, and they kind of follow the same type of curve, how steep it is going to purely depend on what the base is right here. So we're going to have to use all the knowledge we have of transformations, like how to shift stuff, reflect it, all that stuff like we did before. But we're also going to have to be able to understand that the shapes might start just slightly different. One might start a little steeper than the other, so we're going to need a couple more points than we may have needed in the past. Okay? All right, so what we're going to do today is we're just going to write down the parent functions. So this says we're going to split them up into 2 categories. I'm just doing this so you can see the title, and then I'm going to pull it back up. There's growth curves, and there are decay curves. So remember how when you changed the base in your calculator from 2 to 1/3, that instead of going up when the numbers got bigger, it kind of turned around and was getting smaller when the numbers got bigger. So one of those is growth, and one of those is decay. So the first one we're going to talk about is the growth one. The growth one happens when your base, is bigger than 1. So in order for something to be growth, okay, the base is going to be bigger than 1. You can, or you can just continue it on there and make that like your note guide for the chapter. So these are exponential growth curves. They only happen when the base is bigger than 1. So remember, we said that the equation is going to look at just like what we were looking at. And the equation is going to get slightly more complicated in the fact that they could also put a multiplier in here that's like a horizontal stretch or compression, just like this one can be a vertical stretch or compression. None of that stuff is going to change from how it worked before. Okay? But we're just concerned is classifying, first of all, growth curves are the ones where the base is greater than 1. So the ones that we saw with 2 to the x and 5 to the x in the investigation that you did. The things that those two graphs had in common is that they had the point 0, 1, and they had an asymptote at 0. And the curve generally went like this. Now, I'm not saying which one this is, because if this was 5 to the x, it'll look different than if it's 2 to the x, which will look different than if it's 3 to the x. But that's the general shape of anything that has a base greater than 1. So its parent function will always be just this part of it. Okay? And with the base bigger than 1, that means you have an asymptote here at y equals 0. You want to have this reference point at 0, 1. Okay? And you want your curve to go from being very close to 0 through that 0, 1 point and climbing far away from the asymptote and going upward. Okay? Things that will change that, obviously, changing the base will change exactly where it crosses, and then all the stretches, reflections, compressions, shifting, that can all change like normal. Okay? But this is the basic way that these functions will start looking. So this is kind of the basic shape that we want to know for them. Okay? So the asymptote for these, just one asymptote, and it's horizontal. So we don't just write 0, we write y equals 0 so people understand that it's horizontal. Okay? Is this okay with everybody? So new shape is this exponential shape, but it kind of divides up into two categories. The growth category, which the curve goes this way, and then we're going to do the decay category, which the curve goes kind of in the opposite direction. Okay? Yeah. No, b is not the y-intercept. B is the base of the function, okay? So in the investigation we just did, it was 2 sometimes it was 5, sometimes it was 1/3 in the 3 that we did. The ones that would fall into this category of growth would be the ones that have a base of 2 or 5 because the base would be bigger than 1. So I expect those to be shaped like this, a little steeper if it's 5, a little less steep if it's 2. I have to work those points out individually depending on the problem that's given to me. But the general thing I want to know is asymptotes here, main point is here. The other couple points I can't decide till they give me the number I'm using as the base in the problem. Okay? So then the other one that you guys saw, the 1/3, would be in the decay category. So the decay problems have bases that are less than 1 but bigger than 0. Exponential functions don't have negative bases. If you have a negative base, it's a different type of function. It kind of shoots up and down the way it changes values. So that's not what we're focusing on, only positive bases. Okay? So again, the general equation is kind of the same. But the parent equation is just whatever the base is raised to the power of x. But again, that base could be any number. So the decay problem that we saw in the little chart we just did was the ones that had a base of 1/3. So if you look back at your chart and you see how the ones with a base of 1/3 were different from the ones with the base of 2 or 5, they still had this point, and they still had the fact that they approached 0. They just approached it from the other direction. So instead of being really small during the negative numbers that you plug in and getting really big as you plug in bigger powers, kind of had the opposite effect. Got big with the negative powers and got smaller and smaller as you plugged in more positive powers. So anytime that you see an exponential function given to you that has something here like 1/2, 1/3, 2/3, 3/4, some numbers smaller than 1, then you know you're going to have this asymptote, this point at 0, 1, and the shape of your curve is generally going to go this way. But just like with growth, if we change it from a 2 to a 5, it gets a little steeper. Same thing with 1/3 versus 1/4, or 1/3 versus 1/2. And to get the exact numbers besides this point right here, we'd have to use whatever base they gave us in the problem. Okay? And so our asymptote, again, is at y equals 0, and we want to make sure we understand we have that point 0, 1. Okay? So all of our starting points for all the things we're going to graph, people are going to give you problems maybe like this. Okay? This all works how it did before. Out here, vertical reflection, vertical stretch. Okay? Horizontal compression, I can factor it out to see what the horizontal shift is, and I can see the vertical shift. all of that stuff works the same. All the stuff in here is horizontal. All the stuff out here is vertical. But the thing that's different is they can also change this number now. So even though I know the general shape, I have to start each problem differently by whether they give me a 2 or a 5, deciding where those points are going to be before I can stretch, compress them, and reflect them. Okay? So just kind of one added step at the beginning. We can't use the same parent function every time. We'll know the shape of it, but we have to decide the other points based on the base they give us. But all the transformations, once we get the parent function graph, will be the same way we did them in the previous unit, how we stretch, compress, all that kind of stuff. Okay? Does that make sense? Just kind of overview. So tomorrow, you guys don't have any homework tonight.